All right, let's get started. So my goal is to get the exam back to you by Monday. I don't like holding exams for very long, but if I'm being blunt, I do have a little bit of a selfish reason for getting it back to you by Monday because I have an exam in another class on Monday. So I would prefer not to have two exams on my desk at the same time because then it's just a bunch of work and I don't really want to have to deal with that. Okay, so attendance grades are up to date, and for the exam, I just counted everybody present. So I didn't take attendance during the exam, and I usually don't because I have your exams. I know you were there, so I just make sure I have them all, not just count everybody present. I'm still grading homework 2.7, but other than that, everything's up to date. And then 3.1 is going to be assigned today. It will be a very short assignment. I think you'll see what I mean there. All right. Excuse me. Did everybody get the code scanned? Everybody get that? Okay. So today what we're going to do is begin a new unit in the class where we look at rigid bodies. The difference between particle statics and rigid bodies is that in particle statics we assume all the forces go through a common point. That's not the case with a rigid body. And what that means is the potential for a body to rotate and not just translate. And so we are going to introduce the concept of a moment later on. In order to compute a moment, you must multiply vectors. Okay? So we need to talk about that today. What does it mean to multiply a vector? Now I am curious. Is there anybody in here that has not done a cross product before? And it's okay if you haven't. Has everybody seen cross products before? So if you have, cool, which seems like everybody has. Today what I'm going to do is I'm going to present cross products sort of like in a fresh fashion. I'm going to derive the formula for a cross product. I'm not sure, has anybody ever seen a derivation for why we do a cross product the way that we do? If you haven't, then I think you'll appreciate this and understand where it comes from, and I probably do it a little differently than you've seen before. So with that, everybody get the code? Okay, let's get started. Okay. All right, so let's talk about cross products, and mainly what we're talking about is how to multiply two vectors. Okay? Now, if we want to isolate the math from everything that we've been doing so far. Take all the physics and the engineering out of everything that we've been doing for the past few weeks. The first unit of this class is basically about adding vectors. And today, I want to discuss how to multiply vectors. Multiplying vectors, it's going to be important. The reason why is the definition of a moment is a vector multiplication. Now, there are two ways that we could identify a multiplication of vectors. So I have vector A and vector B. I could multiply vector A and vector B and get a number. Okay? I could define that operation. Okay? We call that a scalar product, but the more common way of referring to that is a dot product because we write it like this, right? So A dot B yields a number, whereas A cross B yields a vector, okay? So we have scalar products and vector products, but we more commonly refer to them as dot products and cross products, okay? For those of you that have had experience with dot products and cross products, you'll recognize that dot products are easier. Unfortunately, at least in our world, they're not as useful. Cross products are much more useful, okay? Now, let's talk about goals for multiplication. Okay, multiplication mathematically is what I would call a one-to-one operation, okay? You have a series of inputs, you put them into this multiplication box, and you get a single output, okay? 2 times 3 equals 6, right? Okay? I don't care how many times you do 2 times 3, you get 6. It's not a stochastic operation where I could do 2 times 3 and get 6 and then do it again and get 74, right? So Multiplication by its very nature, we want to be one-to-one. And the same thing is true with vectors, okay? I want to be able to multiply two vectors. So let's talk about cross products. I want to be able to multiply two vectors, and I want to be able to get a definable, predictable result, okay? So how do I do that? How do I reason that through in my head, okay? What are the two aspects that define a vector? What two characteristics must a vector contain? Magnitude and direction. So let's take vector A and vector B, and let's ask ourselves, if I multiply vector A and vector B and I get this product, what is the magnitude of that product? What is the direction of that product? And what is a way that I can define that so that I get predictably the same answer every time? Okay, so I've got here a little animation that I pulled off the web. Okay, so I have here a 3D space that I can sort of rotate at my will, okay? And I want to show you something, okay? So I've got vector A and vector B. Now, what this animation is doing is, as I change, these vectors, see this third sort of, see that vector, that dash vector that's sort of pointing out in space? That is the cross product, okay? So what's happening here, okay? So let's see if we can identify this visually. So what happens if I take the vector and make it longer? If I take the vector and make it longer, suddenly this result gets a lot longer. Like if I take this and make it shorter, the result gets a lot shorter. And the other thing that we see is, as I start rotating these, the product rotates as well. Okay, so how do we do this? So let's talk about direction first. Okay, so does everybody see this little like blue square that tends to move? Does everybody see that? The little blue square that's like sort of moving as I move this one vector? Okay, I propose that if you have two arbitrary vectors out in space, okay, two arbitrary vectors just out in space, that there is a single plane that can be formed with those two vectors. Okay, that's the little blue shaded square that you see right here. And if we want a predictable direction for the cross product, I propose that a predictable direction would be normal to that plane. So no matter which way these vectors face, no matter what the inputs are, the cross product's direction is predictable because we can just say it's normal to that plane. And if you've never heard the term normal, normal just means perpendicular in all directions, right? So if, for example, if here's a plane, this is the whiteboard, this would be normal to it because everywhere it's a right angle. Does that make sense? So that's the direction, okay? Now, as for the magnitude, I propose, and I'm going to get out of this, I propose that for two vectors, those two vectors, we can bound like a parallelogram, like a bounded region between those two vectors. And we can compute the area of that parallelogram. I propose that we can define the magnitude of the cross product to be that area. Does that make sense? Okay? And it is that way, that method, that we can define a unique product for any two vectors. Okay? That the direction is normal to the plane formed by those two vectors, and the magnitude is equal to the area of the parallelogram formed by them. Does that make sense? Is everybody kind of okay with that idea? Has anybody ever heard that before? I'm just curious. Okay. All right. Okay. So, on a side note, one of the ways that we can, if we have two arbitrary vectors in space, we can actually compute the area between, or the angle between them, using this definition of a cross product, assuming we know how to compute a cross product. Spoiler alert, we don't really do this very often because it's a lot easier to compute the area or the angle between two vectors with a dot product, because the dot product is easier to do. But you could do it with a cross product as well. Okay, so far so good? Okay. So one thing I will mention is the right-hand rule, because that will help you define coordinates in 3D. We're going to do really simple right-hand rule stuff today. But the idea with the right-hand rule is if you face your fingers towards the x-axis, curl your fingers towards the y, z points in the direction of your thumb. So like for example, if this is the x-axis and this is the y-axis, we agree that the z-axis probably goes in and out of the board. But the question is the positive z that way or is the positive z that way? Well, face your fingers towards x, curl them towards y, positive z goes like this. Negative z goes like that. Does that make sense? Everybody okay with that? So, it is for that reason, I don't know what happened here. That formula's gone, but I'll write this in. It is for that reason that it's really easy to understand that if you have A cross B and you want to compare it with B cross A, the answer is the signs are flipped, okay? Because the idea is that if you change the order of multiplication, you're changing the order of the right-hand rule, and you're just flipping the directions. And what does a negative sign do to a vector? It just flips the direction on that same line of action. So I propose that if you change the direction or flip the direction of the multiplication, you're flipping the sign of the product. So the cross products are not commutative. Like vector addition was commutative. A plus B equals B plus A. But that's not the case with vector multiplication. A cross B does not equal B cross A. It's the flip sign of that, so it's the negative of it. Everybody okay with that? Okay. Now, you all have probably seen the formula for the cross product before, but where does that formula come from? Like, it's this determinant, and you put the two, and then you cross it that way and cross it that way. Where does that come from? Okay? In order to explain where that comes from, I would like to see if we can understand cross products through the three easiest vectors, I, J, and K. Okay? So I'm going to ask you a simple question. Let's see if we can answer this. What is I cross J? Now, some of you probably know the answer to this question, but if you don't, I'm just curious. Does anybody know what the answer to this is? What is I cross J? This is good. I like this. I like this. This is good. I like it. So let's go off of our definitions. Okay, magnitude and direction. Okay, so let's start off with magnitude. All right, I cross J has an answer. What is the magnitude of this answer? Well, how do we do that? We said that the magnitude is the area of the parallelogram formed by these two vectors, right? Okay, so here's a coordinate system, right? So here's a coordinate system. X, let's redo this. Okay, so this is the y-axis, this is the x-axis. So let's take the I vector. What axis does the I vector lie on? The x-axis. So would you agree that this that might be the I vector? How long is that? 1. Where does the j vector go? The y-axis. So the j vector looks something about like that. How long is that vector? So what does the parallelogram formed by these two vectors look like? It looks like that. What is the area of this parallelogram? 1, right? It's just a square. 1 times 1. So, okay, what do we know about this answer? We know that the magnitude is 1, right? That's what the answer's got to be. What about the direction? Okay, there is a plane formed by the ij vector. Okay, the plane is the xy plane, right? So the direction is normal to the XY plane. Okay? So what is normal to the XY plane? XY, that goes like this. What direction is my marker pointing? Z. So I'm curious, what vector do you all know of that has a magnitude of 1 that points in the positive Z direction? K. So I propose that I cross J equals K. Make sense? Okay. All right. So let's see if we can reason through a couple things. So I cross J is K. Let's see if we can reason through a couple things. What is J cross I going to be?
Negative K.
Negative K. Okay. Here's one that's worth mentioning. What's I cross I going to be?
1.
Well, let's think about that. Okay. What is the area of the parallelogram between I and I?
0.
0. There is no. So I propose that. In fact, let's make this general. What would the cross product be of any vector with itself?
0.
0. See what I mean? We're reasoning through this, right? The cross product of a vector with itself has to be 0. Okay? So I cross I is 0. J cross J, K cross K, they're all 0. Okay? So the reason why I did this is because I put a lot of stuff here on this slide and I want to digest it. Okay? I propose that I cross J equals K. I propose that we can do the same thing with J and K and get I, and K and I and get J. Okay? And similarly, if we flip the signs, we get negatives. And similarly, if we cross a vector with itself, we get 0. Also, there is no angle formed between a vector and itself, so that's another reason these are 0. Okay? Excuse me. A common mnemonic that students will use, and to be honest, I will use, is this. So I'm going to do I, J, K. I'm going to draw a circle in the direction of the alphabet and say that's positive. So instead of having to remember all these formulas, I can use this. Watch this. I cross J equals K. K cross I equals J. But then K cross J, I'm going in the opposite direction, so it's negative I. Does everybody see that? So just go in the direction of the alphabet, and if you're going in that direction, it's positive. If you're going in the other direction, it's negative. Does that make sense? So you don't, like, you could write all this down, but this is a whole lot easier to remember. Everybody with me? Okay. Okay. Any questions? All right. So that's all this is saying right here. So what do we know so far? We know that A cross B points in a direction normal to the plane formed by A and B. And we know that the magnitude of A cross B is equal to that parallelogram. We know how to do this, like the I vectors, cross products of I, J, and K. But how do we compute the cross product of an arbitrary vector? Okay? And the answer is to use these facts. Okay? Now, I got a lot going on here on this slide. So actually, let me hold off on this slide. Let me hold off on this slide, because I'm sure you're seeing that going, what the heck was that? Okay? Bear with me. Can I erase this? Okay. Let's go back to like 4th grade, okay? Or 5th grade. I don't remember. All right, how would you do this multiplication? How would you do that in 4th or 5th grade? So what? This times this, this times this, this times this, and then you would do that times that, that times that, that times that, and then you would do that times that, that times that, that times that. Right? That's how you would do it, right? Okay. So if I had this vector, and then this vector, let's say that I had these vectors, and I wanted to determine P cross Q. So how do I do that? The same way. I do this times this, this times this, this times this, this times this. So I'm going to write a lot here, but bear with me. So what do we got? We've got right? The first terms, the second terms, the third terms. Has anybody ever seen this like this? Curious. Has anybody ever seen this? So, okay, some of you have. Good. Okay. So I'm doing like this times this, this times this, this times this. And I'm preserving the order. So I cross J, I cross K. And then just add it up. So this would really be like a really long equation. I'm just running out of room here on this board, so I'm just putting it on this line. Right? That's what it would look like, right? A lot of steps, but that's what we would get. So, any easy way that we can simplify this? What is this? 0, right? So this term, does everybody have this written down? So we could make that 0. Any other terms we can make 0? This one. And that one, right? Make sense? So 3 of them are going to be gone. Okay? So now, let's see if we can also make things a little easier. Okay. What is I cross J? This is K, right? What is J cross I going to be? Negative K. Okay. What about I cross K? Negative J. Let's see, what about this one? This one's, is it negative I?
Positive.
That's positive I. This one is negative I. This one is positive J. Does everybody see that? So what we'll do is we'll say, okay, let's see if we can simplify this. So a bunch of stuff times I plus a bunch of stuff times j plus a bunch of stuff times k. Okay? And what do we do for the I vector? Let's find all the terms that are associated with I. So PYQZ minus PZQY. For J, what do we get? PZQX minus PXQZ. And then for K, we get PXQY minus PYQX. Yes? Did I get one wrong?
Is I times K supposed? I think you have I and K switch.
No. So if I go I times K, that's negative J. Did I do something wrong?
No, maybe not.
No, you're right.
Yeah, because I cross K is negative J. So this is negative, that term's negative. This term's positive. Am I right? Okay. Does that make sense?
Mm.
Okay. Everybody good? So this next slide that I have here is, like, there's a lot here on the slide, but all I'm doing is this, okay? So if you miss something on the board, don't worry, it's all right here. I just kind of wanted to follow through with that, okay? Does that all make sense? Okay. Does anybody have any questions about this? So I propose, this is the formula, okay? Like if you want to calculate the cross product of an arbitrary vector, this is the answer. This is the absolute answer. The problem with this formula is that it is a pain to memorize. It really is. I don't know that I ever really memorize it until I actually just derive it. You know, that's the only way I would know how to do it. And I don't really want to do that. So because it's a pain to memorize, the question is there a way of simplifying this? And the answer is yes. And the shortcut is to use what's called a determinant. Okay? Do you all remember this in linear or in probably like algebra or something like that? Where if you have a 2 by 2 matrix and I asked you what's the determinant, y'all remember how to compute that? Like this times this minus this times this. Y'all remember that? Does this ring a bell? Has anybody not seen this before? You not seen that? Okay. So this is a determinant is a characteristic of a square matrix. So like not to go down the linear algebra rabbit hole, but determinants will tell you a lot about linear systems. So like for example, remember when we were solving 2 by 2s and 3 by 3 systems of equations? If you take the determinant of those square matrices, those 2 by 2 matrices and those 3 by 3 matrices, and you get a 0, that means the system doesn't have a solution. Okay? So a determinant will tell you in a real quick way whether or not the answer has a, or the system even has an answer. The reason why this is valuable is see this like AD minus BC, see how it sort of mimics the format right here? So we can use determinants to sort of make our life a little easier. Now 2 by 2 determinants are really easy. You just go that times that minus that times that. What about a 3 by 3? Well, 3 by 3 determinants are a little more computationally heavy, and so there's two ways of doing them. The first is to use what's called the rule of Saris. How many of you, when you did a 3 by 3, would take the first two columns, stick them over here, and then say all the products this way minus all the products this way? How many of you have seen that before? Okay, if you've seen that before, the name for that is the rule of Saris. So what you do is you just multiply everything this way, all those products are positive, multiply everything this way, all those products are negative. Okay, that's what's called the rule of Serres. Okay, the other way is to take a determinant and break it up into smaller determinants. How many of you have done it this way? A lot of you have done it this way. Okay, so about half and half. Okay, so the way that it works this way is you pick like a row or column. Typically, you'll pick like the top row, and you'll say, okay, let's take this term, knock out its row and column, and say this determinant. Then take this term, knock out its row and column, this determinant. Then take this term, knock out its row and column, and this determinant. And then you just checkerboard the signs, so positive, negative, positive. And that will give you the answer. Don't worry, we're going to practice this with a numerical example here in a second. Okay? Everybody okay with this? All right. Any questions? All right. I don't normally do math derivations in class, so I want it to be valuable when we do it. Okay, we're going to do a numerical example for the cross product, and we're going to do a really simple one. We're going to compute the cross product of these two vectors. Let me break out the notebook. Where did my thing go? I swear I just had it.
Is it over at the other?
Oh, here it is. It was on my backpack. It's black. My backpack's black, so I missed it. Okay. Sorry. Thank you. All right. So here's the cross product that we're going to compute, and we're going to do it two different ways. Okay. Now I'm going to go ahead and tell you what the answer is to this cross product before we even do any math. Okay. So I propose that A cross B is going to equal negative 2I minus 6J plus 10K. Okay, so that's the answer. Okay, so I'm going to show you two different ways of doing that. Okay, so the first way that we're going to do that is the rule of Serres. And so, again, all these two methods are just sort of shorthand ways of not having to memorize this craziness. Okay, that's what we're trying to avoid. I don't want to have to memorize all that. All right. Okay, so here's our two vectors. A is 2I plus J plus K, and then B is negative 4I plus 3J plus K. Okay? And so A cross B, what we're going to do is we're going to write that in a 3x3 table. Okay? The top row is going to be I, J, and K. The middle row is going to be the first vector, the coefficients, I should say. And so we're going to say 2, 1, and 1. So we're putting a 1 and a 1 because the coefficients here are 1 and 1. And then here we put negative 4, positive 3, and positive 1. Okay? And by the way, for both methods, we do write it in this determinant fashion. Really, what these two methods are simple ways of computing these determinants. Okay? So how does the first method work? Okay? The rule of Serres says what we do is we take this column and this column and write it again. Okay? And then what we do is we take all of our diagonal products this way and make them positive, and all our products this way and make them negative. I mean, look at this equation. How many terms do you have in the equation? 1, 2, 3, 4, 5, 6, like if we were to carry all this out. 3 of them are going to be positive, 3 of them are going to be negative, right? So that's where this is coming from. So what we'll do is we'll say, okay, I'll take this product, and this product and make them positive. So what do I get? I get I times 1, which is I, plus, okay, what do we get? J times 1 times minus 4 is what? Minus 4J. And then this is plus 6K. And then we're going to subtract all of the products that go this way. So if we go left to right, what do we have? We have negative 4K. We get, positive 3I, and we get what? 2J. So let's see if we can like combine this into like collected terms. So let's take the I terms. What do we have? A 1 minus 3, so negative 2. What do we have for the J? We have negative 4 minus 2, negative 6. And then for the K's, we have 6 minus negative 4. So 6 plus 4, which is 10. All right, so that's one way of doing it. How many have never seen that before? Oh, cool. So learn something. That's one way of doing it. That's called the rule of Saris. Okay? One thing I'll tell you, so I'm going to show you 2 ways of doing these cross products, and when it comes to your homeworks and exams, I don't like this homework is the only homework where I'm going to say I want one done this way and one done that way. Past that, I don't care. You can do it however you want. Okay, so I'm not going to micromanage you. So I actually want to give you the flexibility of doing it the way that you want. So far, so good? Okay. Now, the second way, and the name for this is called cofactor expansion. This is not a linear algebra class, so I really don't want to get into like what cofactors are, but suffice it to say they're related to the permutations that you can get in a square matrix when you start doing these types of operations. So, if you've, some of you have probably never seen it this way, so I'm going to take my time with it, okay? So, here's our matrix again. Okay, and I'm going to cheat a little bit. I'm going to cheat a little bit and sort of write this 3 different ways, okay, or 3 different times. Okay. Now, if you've never seen this, I think this will help. Okay. So what we're going to do is we're going to the term is we're going to expand this along the top row. So what we're going to have is a cofactor for each term on the top row. So a cofactor for the I term, a cofactor for the J term, and a cofactor for the K term. So I'm going to show you how we're going to do that. Okay? So what we do is this. Okay? If we're focused on the I term, what we do is we cross out or eliminate the row and the column that's associated with I. And what we're left with is a 2x2 determinant, which we can solve using this, which is really, really easy to remember. Just that minus that. If we're looking at the J term, we cross out the row and column associated with J, and we're left with 2, negative 4, 1, 1. And then for K, we cross out the row and the column associated with K, and we're left with this. So the idea is that if we want to determine the cross product, we just have the I term multiplied by this, the J term multiplied by this, the K term multiplied by this. Okay, so it's pretty straightforward. So what I can do, if you don't mind, I'm gonna do that a little bit. I can say, so therefore, A cross B equals I times that first one, J times that second one, and K times this one. And then in terms of the signs, like the positives and negatives, what you basically do is positive, negative, positive. Okay? So you can say, all right, I times what? Okay? So how do we do this? Well, it's 1 times 1 minus 1 times 3. So here, I'll just write it out because I think that might be easier. Then minus J, 2 times 1 minus 1 times negative 4 plus K, 2 times 3 minus 1 times negative 4. So what do we get? 1 minus 3, negative 2, minus J times 2, what is that? 2, what is it? 2 minus negative 4 is 6, plus K, and then 6 minus negative 4 is 10, or negative 2I minus 6J plus 10K. Same answer. How many of you have never seen it that way? Okay, all right. So everybody learned something. Cool. I don't like doing a lot of derivations in this class, but where it's important, I feel like we should take the time and do it. We're going to be doing a lot of cross products in here, and I do want it to come naturally. So I don't want to just barrel through and say, oh, you all know how to do this. I don't want to be that professor. So I thought it worthwhile that we all are on the same page. And even those of you that had done them before, it felt like you learned something. So that's good. So here's what we're going to do. I'm going to give you two vectors. I'm going to give you some vectors. Multiply it, like some vectors using the rule of Serres, some vectors using cofactor expansion. It's two problems. I think they're two different sets of vectors. So it's like do A cross B this way and do C cross D that way or something like that. So shouldn't be a very long assignment. Yes?
So there's two problems. Do you want them done like one problem both ways, one problem both ways?
No, it's just one rule of Serres, one cofactor.
Okay.
Just, yeah. And again, so one thing I will mention this course, I will probably do this method more often, like in-class problems. I like it. That's just sort of my way. I think it's easier to track the signs. But if you like the first method better, or that's what you learned when you first started doing this, you do that too. I don't care. You do whatever works for you, okay? Sound good? We'll start with moments next time.